Welcome to the ASIC-LS tutorial series, Analog IC Engineering for Engineers. My name is Robbie Robinson and I'm a Director of ASIC Layout Services. In this tutorial I want to demonstrate the LATCHUP mechanism and how it forms in CMOS. First of all, we show the silicon substrate profile of an inverter, and in it we'll define our N-well implant, which we mark N-. We also mark the substrate P-. The minus in both cases means low dope. Then we show our P-type transistor being formed in the N-well by two P+ implants. P+ indicates highly doped. And of course now we show the gate. We'll mark this drain, gate and source. Next we'll show the N+ implant, also called N-tap, being defined in the N-well. N+ makes good contact to N-, and we'll also show the metallization, which we'll use in a moment, to connect up to VDD. Next we'll switch to the N-type transistor, which we define in the P-well, or substrate. We do this with two N+ implants, and again we form the transistor by bridging the two N+ implants with the gate. We mark this drain, gate and source. Here we're showing the P+ implant, which forms a good contact to the substrate, and then we'll use again some metallization, which we'll use to connect VSS via the P+ P-tap to the substrate so that the substrate is tied low. So let's connect the N+ implant to the lowest metal, metal 1, and also connect metal 1 to VDD. The reason we do this is because the N-well forms a diode with the substrate, so we've ensured that by connecting it to VDD that we've reverse biased this diode. We also connect the source of the P-type transistor to VDD. Now we'll connect the source of the N-type transistor and the P-tap to VSS, tying them both low. Then if we tie the two drains together, we can show the output from this profile of an inverter. And if we connect the two gates together, we show the input to this profile of an inverter. Next we'll mark our P-type transistor P1 and our N-type transistor N1. And now let's look at how the retrograde N- and P- wells, in combination with the N+ and P+ implants, form parasitic transistors which will lead to LATCHUP. First of all, we draw our NPN parasitic bipolar transistor. Then we draw our PNP parasitic bipolar transistor, and we show the connection of the collector of the NPN to the base of the PNP, and here we're showing the R-well resistance which connects to the VDD supply. Next we'll show the PNP transistor collector which connects to the base of the NPN transistor, and here we're showing the R-sub connection to VSS. Now let's switch to the schematic representation of these parasitic bipolars which are forming our LATCHUP mechanism. First of all, we show VDD. Next we'll draw R-well. And then we'll show N1. Now we'll draw VSS. Now we'll draw P1. And of course, here we'll draw our sub. the base of P1 connects to the collector of N1, and the base of N1 connects to the collector of P1. Now let's look at how latch-up occurs when we get a surge on VDD. We can see that the emitter of P1 becomes forward biased, so P1 switches hard on, so the potential on the top of our sub rises, and so the potential at the base of N1 rises, and so N1 is turned hard on. This means that the base of P1 is effectively connected to VSS, and again it is switched hard on, and so we have latch-up. This latch-up trigger can also be caused by a negative pulse on VSS.